Good morning, students. In the last module, we studied ways to manipulate and measure vectors, projection of vectors, and linear mappings. In this module, we will study three aspects of matrices: how to summarize matrices, how matrices can be decomposed, and how these decompositions can be used for matrix approximations. So we first consider methods that allow us to describe matrices with just a few numbers that characterize the overall properties of matrices. We will do this in the section on determinants and eigenvalues. So our first topic is determinants. Determinants are defined for only square matrices, and it is a function that maps the matrix into a real number. So determinants are important concepts in linear algebra. A determinant is a mathematical object in the analysis and solution of systems of linear equations. And I have already said that determinants are only defined for square matrices, that is, matrices with the same number of rows and columns. So we write the determinant as A11, A12, etc. A1n, A21, A22, etc. A2n, etc. AN1, AN2, etc. ANn. We can represent the determinant as determinant of A or A within two vertical bars. So there is a theorem. For any square matrix, A is an element of R n by n. It holds that A is invertible if and only if determinant of A is not equal to 0. And one more thing, for a diagonal or upper triangular or a lower triangular matrix, the determinant is the product of its diagonal element. So we will see an example. That is, determinants can be used to measure the volume. If the two sides of the parallelogram is represented as two columns of a matrix, then the absolute value of the determinant represents its volume. Similarly, for a parallel pipe with three sides RBG, then determinant of a 3 by 3 matrix RBG sides is the volume of the solid. We will see an example. Consider the three linearly independent vectors RGB is an element of R3. R is equal to 20 minus 8, G is equal to 610, and B is equal to 14 minus 1. So first of all, write these vectors as the columns of a matrix. So A is equal to determinant of RGB. So 261014 minus 80 minus 1. Then compute the determinant of this matrix and we will get 186 as the desired volume. Computing the determinant of an n by n matrix requires a general algorithm to solve the cases for n greater than 3, which we are going to explore here. So Laplace expansion is a theorem which can be used to reduce the problem of computing the determinant of an n by n matrix to compute the determinant of n minus 1 by n minus 1 matrices by ultimately computing determinants of 2 by 2 matrices. So according to this theorem, consider a matrix A is an element of R n by n. Then for all j is equal to 1 to n, expansion along column j, determinant of A is equal to, we can use this equation, summation of k is equal to I to n minus 1 raised to k plus j, akj into determinant of akj. And we can also write expansion along row j, that is determinant of A is equal to summation of minus 1 raised to k plus j, ajk into determinant of ajk. Here, akj is an element of R, n minus 1 by n minus 1 is the submatrix of A that we obtain when deleting row k and column j. We will see an example. So here, there is a 3 by 3 matrix. We will use Laplace expansion to find the determinants. So here A is equal to 1, 2, 3, 3, 1, 2, 0, 0, 1, which is equal to minus 1 raised to k plus j. So 1 plus 1 into akj, 1 into 1201 plus minus 1 raised to 1 plus 2 into 2 into determinant 3201 plus minus 1 raised to 1 plus 3 into 3 into determinant 3110. Then we will get minus 5 as the determinant. So we will now see the properties of determinants. For A is an element of Rn by n, the determinant exhibits the following properties. First one is determinant of AB is equal to determinant of A into determinant of B. Determinant of A is equal to determinant of A transpose. Determinant of A inverse is equal to 1 by determinant of A. Similar matrices possess same determinant. So the determinant is invariant to the choice of basis of a linear mapping. Adding a multiple of row or column to another does not change determinant of A. Then multiplication of a column or row by a scalar k scales the determinant by k. Then swapping two rows or columns changes the sign of determinant of A. Because of the last three properties, we can use Gauss elimination to compute determinant of A by bringing A into row echelon form. We can stop Gaussian elimination when we have A in a triangular matrix, where the elements below the diagonal are all 0. And remember, the determinant of a triangular matrix is the product of the diagonal elements. The square matrix A is an element of R n by n has determinant of A not equal to 0 if and only if rank of A is equal to n. In other words, A is invertible if and only if it is full rank. Trace. The trace of a square matrix is defined as trace of A is equal to summation of AII. That is, trace is the sum of the diagonal elements of A. So now we will see the properties of trace. First property is trace of A plus B is equal to trace of A plus trace of B. Then trace of Ka is equal to K into trace of A, where K is a scalar. Then trace of I is equal to N. Then trace of AB is equal to trace of BA. Trace of ABC is equal to trace of BCA invariant under cyclic permutation. Then trace of X Y transpose is equal to trace of Y transpose into X is equal to Y transpose X. If A is a transformation matrix for a linear mapping for a different base B, A is equal to S inverse AS. Trace of A is equal to trace of S inverse AS. That is, trace of S inverse A is equal to trace of A. This shows that trace is independent of the basis in linear mapping. So we have covered determinants and traces as functions characterizing a square matrix. So taking together our understanding of determinants and traces, we can now define an important equation describing a matrix A in terms of a polynomial, which we will use extensively in the coming sections. So for that is characteristic polynomial. For lambda is an element of R and the square matrix A is an element of R n by n, the characteristic polynomial Pa of lambda is equal to determinant of A minus lambda I is equal to C0 plus C1 lambda plus C2 lambda square plus etc. up to Cn minus 1 lambda n minus 1 plus minus 1 raised to n lambda n. The characteristic polynomial will allow us to compute eigenvalues and eigenvectors. So in the characteristic polynomial, C0 is equal to determinant of A and Cn minus 1 is equal to minus 1 raised to n minus 1 into trace of A. We will see an example. Let A is equal to 2, 1, 1, 2. The characteristic polynomial Pa of lambda is equal to determinant of A minus lambda I. is equal to 2 minus lambda 1, 1 and 2 minus lambda is equal to 2 minus lambda the whole square minus 1 is equal to 2 square minus 4 lambda plus lambda square, that minus 1 is equal to 3 minus 4 lambda plus lambda square. Note that the determinant of the matrix, determinant of A, is equal to 3, that is equal to C0, and the trace of the matrix, trace of A is equal to 4, which is equal to minus 1 raised to n minus 1, Cn minus 1 is equal to minus 4. Our next topic is eigenvalues and eigenvectors. Eigenvalues are associated with eigenvectors in linear algebra. Both terms are used in the analysis of linear transformations. Eigenvalues are the special set of scalar values that is associated with the set of linear equations, most probably in the matrix equations. The eigenvectors are also termed as characteristic roots. It is a non-zero vector that can be changed at most by its scalar factor after the application of linear transformations. And the corresponding factor which scales the eigenvectors is called an eigenvalue. So eigenvalues are the special set of scalars and it is associated with a system of linear equations. It is mostly used in matrix equations. Eigen is a German word that means proper or characteristic. Therefore, the term eigenvalue can be termed as characteristic value or characteristic root, proper values or latent roots as well. In simple words, the eigenvalue is a scalar that is used to transform the eigenvector. So the basic equation is Ax is equal to lambda x. The number of scalar value lambda is an eigenvalue of A. So in mathematics, an eigenvector corresponds to the real non-zero eigenvalues which point in the direction stretched by the transformation, whereas eigenvalue is considered as a factor by which it is stretched. In case if the eigenvalue is negative, the direction of the transformation is negative. For every real matrix, there is an eigenvalue. Sometimes it might be complex. The existence of the eigenvalue for the complex matrices is equal to the fundamental theorem of algebra. So the following statements are equivalent. Lambda is an eigenvalue of A, is an element of R n by n, and there exists an x is an element of R by n set of 0 with Ax is equal to lambda x, or equivalently A minus lambda I into x is equal to 0 can be solved non-trivially, that is x not equal to 0, and rank of A minus lambda I is less than n, and determinant of A minus lambda I is equal to 0. Next topic is collinearity and codirection. So two vectors that point in the same direction are called codirected, and two vectors are collinear if they point in the same or the opposite direction. If x is an eigenvector of A associated with eigenvalues lambda, then for any C is an element of R0, it holds that Cx is an eigenvector of A with the same eigenvalue, since A of Cx is equal to C into Ax is equal to C lambda x is equal to lambda into Cx. Here Ax is equal to lambda x. Thus, all vectors that are collinear to x are also eigenvectors of A. So, for lambda is an element of R and a square matrix A is an element of R n by n, Pa of lambda, the characteristic polynomial, is equal to determinant of A minus lambda I is equal to minus 1 raised to n lambda raised to n plus C n minus 1 lambda raised to n minus 1 plus etc. C2 lambda square plus C1 lambda plus C0. So the characteristic polynomial will allow us to compute eigenvalues and eigenvectors. In the characteristic polynomial, C0 is equal to determinant of A and Cn minus 1 is equal to minus 1 raised to n minus 1 into trace of A. So lambda is an element of R, is eigenvalue of A is an element of R n by n if and only if lambda is the root of the characteristic polynomial. The algebraic multiplicity of lambda I is the number of times the root appears in the characteristic polynomial. Now we will see the eigenspace and eigenspectrum. An eigenspace of vector x consists of a set of all eigenvectors with the equivalent eigenvalue collectively with a zero vector. It is denoted by E lambda, where lambda is the eigenvalue. The set of all eigenvalues of A is called eigenspectrum or spectrum of the matrix A. If lambda is the eigenvalue of A, then the corresponding eigenspace E lambda is the solution space of the homogeneous system of linear equation A minus lambda I into x is equal to 0. Geometrically, the eigenvector corresponds to a non-zero eigenvalue points in a direction that is stretched by the linear mapping. The eigenvalue is the factor by it is stretched. If the eigenvalue is negative, the direction of the stretching is flipped. Now we will see the properties. A matrix A and its transpose A transpose having the same eigenvalues but not necessarily the same eigenvectors. Eigenvalues will be same, but the eigenvectors may be different. The eigenspace is the null space or kernel of A minus lambda I. Similar matrices having same eigenvalue. Therefore, linear mapping matrix has an eigenvalue that is independent of the basis. Symmetric positive definite matrices always have positive real eigenvalues. Now, the determinant of a matrix is the product of its eigenvalues. The trace of a matrix is the sum of its eigenvalues. So Ax is equal to lambda x. So A inverse Ax is equal to A inverse into lambda x. That is A inverse x is equal to 1 by lambda into x. That is eigenvalues of A inverse is 1 by lambda. Ax is equal to lambda x. So A square x is equal to lambda square x. That is in general A raised to kx is equal to lambda raised to kx. Now, in the case of identity matrix, the identity matrix has characteristic polynomial 1 minus lambda raised to n is equal to 0, which has only one eigenvalue, that is lambda is equal to 1, that occurs n times. Moreover, Ix is equal to 1x holds for all vectors. Because of this, eigenspace spans all the dimensions and all standard basis vectors of R and are eigenvectors of I. Now we will see the applications of eigenvalues and eigenvectors. Eigenvalues and eigenvectors play a significant role in various aspects of machine learning. Some of the key applications of eigenvalues and eigenvectors in machine learning are: the first one is dimensionality reduction. One of the most common applications of eigenvalues and eigenvectors in machine learning is in dimensionality reduction techniques like principal component analysis (PCA). It finds the principal components of eigenvectors of the data, which are the directions along which the data varies the most. The corresponding eigenvalues indicate the amount of variance captured by each principal component. By retaining only the top eigenvalues and their corresponding eigenvectors, PCA allows for effective dimensionality reduction. Then, image compression. Eigenvalues and eigenvectors are used in image compression techniques like singular value decomposition (SVD). This decomposes an image matrix into its constituent eigenvalues and eigenvectors. By keeping only the most significant eigenvalues and their corresponding eigenvectors, images can be efficiently compressed without losing critical visual information. Spectral clustering is a powerful technique used in unsupervised learning to partition data into clusters. Eigenvectors corresponding to the smallest eigenvalues provide information about the cluster structure of the data. Collaborative filtering in recommender systems can use the concepts of eigenvectors to identify the latent factors and represent user-item interactions in lower dimensional spaces. This helps in making personalized recommendations efficiently. In natural language processing tasks like topic modeling or latent semantic analysis, eigenvectors can be used to identify latent topics or dimensions in the text data, making it easier to discover underlying structures and patterns. In graph-based machine learning algorithms, eigenvectors are used to calculate centrality measures such as page rank in web graph analysis, which helps to rank web pages based on their importance. In some neural network architectures, such as autoencoders, the hidden layers activations correspond to the eigenvectors of the covariance matrix of the input data. So understanding the eigenvectors can provide insights into the network's internal representations and how it captures relevant features in the data. In summary, eigenvalues and eigenvectors have diverse applications in machine learning, ranging from dimensionality reduction and clustering to image compression and graph analysis. They enable efficient data representation, feature extraction, and structure discovery, making them powerful tools for understanding and processing complex data in various machine learning tasks. The next section is computing the eigenvalues, eigenvectors, and eigenspaces. The first step is to find the characteristic polynomial, then compute the eigenvalues, and third step is to find the eigenvectors and eigenspaces. So we will see an example. Find the eigenvalues and eigenvectors for A is equal to 6, 4, minus 3, minus 1. So what about the solution? If Ax is equal to lambda x, then A minus lambda, determinant of A minus lambda I is equal to 0. So A minus lambda I is equal to 6 minus lambda 4, minus 3 and minus 1 minus lambda. So taking the determinants on both sides, we get the characteristic polynomial. So 6 minus lambda into minus 1 minus lambda plus minus 3 into 4 is equal to 12 is equal to 0. So lambda square minus 5 lambda plus 6 is equal to 0. So lambda minus 2 into lambda minus 3 is equal to 0. Therefore, the eigenvalues are lambda is equal to 2 and lambda is equal to 3. To find the eigenvectors, we substitute the eigenvalues into the equation A minus lambda I into x is equal to 0 and find the null space of the left LHS. For the eigenvalue lambda is equal to 2, we have 4, 4, minus 3, minus 3. So the first row gives x1 is equal to minus x2. So that the eigenvector corresponding to the eigenvalue lambda is equal to 2 is x is equal to 1 minus 1. For the eigenvalue lambda is equal to 3, we have a minus lambda I is equal to 3, 4, minus 3, minus 4. So solving this will keep the first row as 3x1 is equal to minus 4x2. So that an eigenvector corresponding to the eigenvalue lambda is equal to 3 is 3 minus 4. Typically, we want to normalize the eigenvectors, that is, find unit eigenvectors. We get v1 is equal to 1 by root 2 minus 1 by root 2 and v2 is equal to 3 by 5 minus 4 by 5. Now, the next section is geometric multiplicity and algebraic multiplicity. Let lambda I be an eigenvalue of a square matrix A, then the geometric multiplicity of lambda I is the number of linearly independent eigenvectors associated with lambda I. The algebraic multiplicity specifies how many times the eigenvalue lambda I occurs. So a specific eigenvalue's geometric multiplicity must be at least 1 because every eigenvalue has at least one associated eigenvector. An eigenvalue's geometric multiplicity cannot exceed its algebraic multiplicity, but it may be lower. So we will see an example. The matrix A is equal to 2, 1, 0, 2 has two repeated eigenvalues, that is lambda 1 and lambda 2 is equal to 2, and the algebraic multiplicity is 2. The eigenvalue has only one distinct unit vector, x1 is equal to 1, 0. So the geometric multiplicity is 1. Now we will see what eigenbasis is. This theorem states that eigenvectors of a matrix with n distinct eigenvalues form a basis of Rn. That is, the eigenvectors x1, etc., xn of a matrix A with n distinct eigenvalues lambda 1, lambda 2, etc., lambda n are linearly independent. And a square matrix A is said to be defective if it possesses fewer than n linearly independent eigenvectors. Spectral theorem. Given a matrix A is an element of Rn by n, we can always obtain a symmetric positive definite matrix S is an element of Rn by n by defining S is equal to A transpose A. If rank of A is equal to n, then S is equal to A transpose A is symmetric and positive definite. This theorem holds is insightful for how we can use symmetrized matrices. Symmetry requires S is equal to S transpose, and by inserting it into this equation, we obtain S is equal to A transpose A is equal to A transpose into A transpose the whole transpose is equal to A transpose into A the whole transpose is equal to S transpose. Positive semi-definiteness means this requires X transpose Sx should be greater than or equal to 0. That is, X transpose Sx is equal to X transpose into S is equal to A transpose A. So A transpose A into X is equal to X transpose A transpose into Ax, which is equal to Ax transpose into Ax. That should be greater than or equal to 0. The dot product is sum of squares which are non-negative. So if A is an element of Rn by n is symmetric, then there exists an orthonormal basis of the corresponding vector space V consisting of eigenvectors of A, and each eigenvalue is real. So a direct implication of the spectral theorem is that eigen decomposition of a symmetric matrix A exists, and we can find orthonormal basis of eigenvectors so that A is equal to PD P transpose, where D is the diagonal matrix with eigenvalues and columns of P contains eigenvectors. Eigen decomposition will be discussed later. The eigenvectors associated with the same eigenvalues are not orthogonal, and the geometric multiplicity should be greater than 1, and we can use Gram-Schmidt algorithm for orthogonalization in this case. And now we will see the relationship between determinants and trace. The determinant of a matrix is the product of its eigenvalues. That is, determinant of A is equal to product of I is equal to 1 to n lambda I. That is, lambda 1 into lambda 2 into etc. lambda n. The trace of a matrix is the sum of its eigenvalues, that is, summation of lambda I, that is lambda 1 plus lambda 2 plus etc. lambda n, where lambda is the eigenvalue. Now we will see a problem. Compute the eigenvalue and eigenvectors of A. So A is equal to 1, 0, 1, 1. And first of all, find the characteristic polynomial by finding the determinant of A minus lambda I. So here we got 0. It's the characteristic polynomial. So lambda is equal to 1 is the only root of P, and therefore the only eigenvalue of A. So to compute the eigenspace, we need to compute the null space. That is A minus 1 into Ix is equal to 0. That is 0, 0, 1, 0 into x is equal to 0. So the only eigenvector is E1 is equal to 0, 1. When lambda is equal to minus 3, the null space of A minus lambda I is A minus lambda I is equal to 1, 2, 2, 4. That is E1 is equal to 2 minus 1 and is the eigenspace corresponds to the eigenvalue lambda is equal to minus 3. When lambda is equal to 2, the null space of A minus lambda I is A minus lambda I is equal to minus 4 to 2 minus 1. That is E2 is equal to 1 by 2, 1. And is the eigenspace corresponds to the eigenvalue lambda is equal to 2.